Welcome to the Austin Forum Upload, the podcast of the Austin Forum on Technology and Society. I'm Jay Boisseau, the Executive Director and founder of the Austin Forum. And I'm here with three of my colleagues and friends today. I'm very pleased to have Mike Ignatowski of AMD, John Lockman of Dell Technologies, as well as also the Austin Forum, and Fernanda Forder of Voltron Data. Guys, thanks for joining me on the podcast today.
Hey, thanks for having us on.
Glad to be here.
Yeah.
All right. So today's topic is the state of supercomputing, or high performance computing, as it's more commonly called. And that's our topic today because the largest conference in the field of high performance computing just happened a couple of weeks ago, right before Thanksgiving. And I was not able to attend this time after attending over 25 previous annual conferences. So I've asked you all on this podcast, in part to educate our listeners, and in part to help catch me up on what I missed at SC23 this year. So we'll jump right in with self-intros. So John, why don't you give a quick self-intro? A lot of our listeners already know you, but maybe give a self-intro from the perspective of your HPC side.
Yeah, John Lockman. And I spend a lot of my time these days looking at the future of HPC and AI software, automation tools, programming tools, frameworks, and so supercomputing is always a really good conference, to really kick off a lot of new ideas.
And for our listeners who don't know, John is also our technology director for the Austin Forum and the producer of these podcast episodes. So he's the one that makes them sound so professional. Mike Ignatowski, how about you self-introduce next? And I'll just do a quick preface there and say for our listeners, Mike is also involved with the Austin Forum as the advisory board member from AMD. Mike?
Yeah, thanks, Jay. So I'm a senior fellow at the AMD Research and Advanced Development Group here in Austin. Our company makes chips ranging from the ones that power the PlayStation and Xbox all the way up to some of the largest supercomputers in the world. And I've been attending supercomputing now for about 10 years and thoroughly enjoy it.
And Fernanda.
Hey, folks. I've been working at Voltron Data for a couple of years now, and my background is in the Department of Energy. I've been at Oak Ridge National Lab. I've been at NVIDIA. I've done consulting. I basically don't know what I want to do when I grow up, and I keep following interesting problems and changing jobs along the way because everything's so interesting in supercomputing. And this past supercomputing was my 15th year. My first supercomputing was in 2009.
Well, great. First of all, I'm envious that all three of you went this year, and I had obligations that kept me from going. I'm also sad that I didn't get to see all of you this year at SC, but thanks for joining me today. So for our listeners, probably what we should start with, just to make sure everybody's on the same page, is a quick explanation of what supercomputing means. And I'm going to ask each one of you to give me your quick definition, but in a different context. So, John, when you're out and about with your friends on the town, how do you explain to them between beers what supercomputing is?
Supercomputing is the best of the best, and sometimes even cooler than what's out there on the regular, available to the regular folks. It's always the sort of the highest performance in everything, whether that's CPU or network or power usage or size. It's sort of the Formula One racing of computing.
Great. Fernanda, how do you describe it to your friends and to colleagues?
I generally think about it from the problem perspective. It's everything in supercomputing that I see in supercomputing is what is the biggest simulation that I can do given the computing power that I have now? What's the biggest problem that I can solve computationally given the computing power that I have now? And often computers get built to try to meet these demands, and that's how I define supercomputing. It's basically I am doing the best that I can given the supercomputing, or even given the hardware available at the moment. And some of the hardware that gets installed is serial number 0. And so we're getting the very best before even the rest of the public gets it.
All right. And Mike, how do you convince all of your colleagues at a place like AMD that makes processors for PlayStations and laptops and desktops? How do you explain supercomputing to them?
Well, we describe it as pushing the boundaries of everything in the technology area. And we contrast that to other large data centers. Google has this huge data centers around the world to do web searches, and Amazon has huge data centers to do online shopping. And what we do is very large, very high power systems to do advanced scientific calculations, lots of simulation, lots of modeling of climate change, efficiency, and so on. Focusing on the scientific calculations, not web searches and shopping.
All right. And I'll share my own definition because I get to describe it to my friends and colleagues a lot too. And it really does borrow from all of yours. I try to describe it as taking computers and integrating them together to act as a more powerful, faster, larger memory virtual computer, something that can solve the important problems with better accuracy, better speed, better scale, et cetera. So kind of in line with Fernanda, it really is about the problems you need to solve. And you don't need to solve every problem on a supercomputer, but there are many interesting problems that can only be solved on high performance computing clusters, scaling up to what we might think of as supercomputers. And with that, I'm going to ask each of you, what is a great example in your mind of an application or a problem that requires supercomputing that our listeners need to realize they're not going to be able to run it on their laptop or their desktop? It really requires this massive supercomputer in a big data center somewhere. And Mike, I'll start with you on this.
Well, certainly I'll point to the climate modeling as one of the very important ones that are done on supercomputers. An interesting one that was described to us at this year's supercomputing conference was a certain manufacturer of jet engines. They have a design for a new complex jet engine that's at least 20% more energy efficient than anything out there in the market. And they're trying to study this with advanced simulations, do lots of calculations of airflow and turbulence. And it takes right now several months to do that simulation on a large supercomputer. And they would want to get that down to a couple of days so they could test a design, look at the results, refine it, and come back a couple of days later and run a new variation on that. So those are some of the interesting things they were talking about this year.
All right. How about you, John? What are your application areas you like to share as drivers for the importance of supercomputing?
I think, like Fernanda said, it's the grand challenge problems that we talk about. Energy, drug discovery, climate. Those are all the big, the big grand challenges that we're looking to solve, and we can't do those on a laptop in any reasonable time. You can't do it on a single server. You can't fit that much memory or that much computation into a single box. Those are kind of the cool applications that I look at is, drug discovery, energy, whether that's oil and gas discovery, or even looking at other really cool new ways of generating energy. Everything from your wind turbine to solar panels are all designed on large scale supercomputers. So I think those are the kind of neat things that we look at in how do we solve these really big problems is we build these huge systems, and I think that's kind of the coolest part about supercomputing is we just keep asking more questions. And if we come to an answer, we find an answer, we might say, that's good enough for now, but I'd like higher resolution next year. Can we build something bigger and bigger and even more optimal to help solve some of those problems?
All right. And Fernanda, we'll close this round with you before we get into our general conversation, which is, what applications do you like to tell people are so important that they need investments in supercomputing?
I like to keep it down to what folks need every day. And for me right now, the examples that I use for like my mom, or family members that don't quite understand why do we build a computer this large? What does it mean to have an exascale computer? It's things like batteries, right? Do you enjoy, your battery would you like to have a battery in your vehicle so you wouldn't have to fill it with gas all the time? Would you like to have a battery in your house so that you could fill it up with solar power and not depend on the the power company when power goes out because a hurricane hit. I'm from Florida, so that's one of the things that come up. Do you like your home structure to stay intact? So all of these things are specific types of simulations that get run. They're either material simulations or they're what we call computational fluid dynamics. So how air moves, how fluids move, right? In any sort of kind of fluid, how do they move? It could be a fluid moving back out, into the earth. How do we put carbon back into the earth? Those are all important things coming up in people's everyday. We're talking about climate change every day. So all of these problems are everyday challenges, and that people, want to see an improvement in. I want to buy an electric car, but I have range anxiety. I want to, get solar panels, but I'm not sure I'm going to get the efficiency that I'm going to get. And all of those things are day-to-day discussions and decisions that people are making on their daily life. So I try to keep it to their daily life. How does this impact you in your daily life? And it's easy to say like drug discovery, but they've been listening to this for 20 plus years. But I can point to real efficiencies in transportation. I can point to real efficiencies in battery manufacturing and improvement of the battery. I can say, look, your battery's gotten a lot better, right? And remember when laptops only lasted like 2 hours? And now how long does your laptop last? All of that came out of simulations on the supercomputer, and they can generally understand that.
Yeah, I look at the weather simulation side. I remember moving to the Texas coast in the early 2000s, and a hurricane would come in, and that model would show it's going to hit somewhere between Florida and Mexico.
Right.
Spaghetti models all over.
Gulf
and
Coast, evacuate.
It will be here. And, you look
right.
just to 20 years later and how accurate they can get that cone. And so you don't have to have everybody evacuate, and exactly who needs to. Those are really good real world things to show how supercomputing is continuing to advance.
Yeah, I always use the weather example because if you can't predict the weather, you can't save lives, property, take the proper precautions, et cetera. And so severe weather is sort of that elevator pitch for the need for supercomputing. You've got to be able to compute an approximation of the weather far before it actually happens. So it's got that time urgency as well as that accuracy requirement. And of course, that large scale memory problem size requirement because you're simulating the weather over a very large region. So I'm with you. I love giving those practical examples. I even do it with, from the moment you leave your house, you get in your car was designed on a supercomputer and crash tested there. The weather forecast you read, calculated on a supercomputer, and so on.
So one of the coolest factoids I like to throw out as someone that worked in the Summit project at the DOE at the Department of Energy is that the same supercomputers or the same nodes that went into the Summit supercomputer running simulations in yourweather.com, which was purchased by IBM, the same exact supercomputing node, the same exact applications run by weather.com so that you can see your weather. And people can go like, oh, really? I mean, I literally have access to some result from a supercomputer on my hand. That gets people pretty excited.
Yeah, you do kind of have to remind them that when they open their smartphone and click on the weather app and see a 7-day forecast, that it wasn't the smartphone that calculated that weather forecast.
Right.
It was a supercomputer that calculated it somewhere, and then it got relayed to their phone. But yeah, I love the weather example. Okay, let's jump into SC23 since I missed it, and it represents the state of the art in supercomputing. I'd like to hear from each of you in any order. What was something really exciting at SC23 this year that was achieved recently, or a direction that you see things going? So any of you feel free to jump in.
So 14,000 people attended SC, over 14,000 people. That's a record-breaking attendance. And, post-COVID, I think the first one in 21 was somewhere between, I think, 1,500 people or less. And then after that, it was maybe like 6,000 or 7,000 people. And to have, not only a full room, but everybody was there and all the vendors were there. And it felt like we were back. So that was great. And the second part of it was the announcement that part of Aurora had finally been installed, and Aurora is the supercomputer that we've been waiting on for 5 to 6 years now. And due to many things that we could probably go into more detail about Intel being able to deliver or not being able to deliver, but the fact that some of it was delivered and they were able to actually run a benchmark on it and give us a number and say, hey, it's alive, it's coming. That's been great.
And for our listeners, Fernanda's referring to Aurora, a supercomputer at Argonne National Laboratory. You'll hear throughout this conversation mention of DOE labs in particular, because these Department of Energy labs deploy among the most powerful supercomputers in the world. And that's one, as Fernanda said, we've been waiting on for years. So that's exciting that some of it's deployed at least.
That's right. Yeah. I mean, we were all surprised that numbers came out, but we were happy surprised. No one wants to see a supercomputer fail. And the fact that it did put out a number was a good thing.
So I'll build on that a little bit. One of the big events at supercomputing each year is the announcement of the top 500 supercomputers in the world. There's an organization that tracks that list every year. And the top computer on there was at Oak Ridge National Lab. It's called the Frontier computer. And I'll brag a little bit because the components for that were built by AMD, and something we've been doing research on it for a long time. We had to partner with HP, Hewlett Packard, to basically put them all together in a big system and provide the interconnect network. But that Frontier system was the first computer to achieve an exascale performance, which is 10 to the 18th calculations every second. That's still number one on the top 500 list. The Aurora supercomputer was number two. And interestingly, number three that people did not expect was a assembly of components from Microsoft in their cloud computer. And we didn't see that one coming, but that is an interesting non-DOE National Lab entry into the top 500 that kind of foretells what might be happening in the future as we move forward.
Yeah, that was a really interesting announcement. It caught me off guard too. But in a way, it's not very surprising. So these cloud data centers, as you mentioned earlier in the podcast, have lots of computing equipment in them. They're just not integrated as supercomputers in most cases, using the very fastest components, as John mentioned earlier in the podcast, and the very fastest networks and the special purpose software that make all these individual servers act like a supercomputer. So I love that these cloud providers, though, are embracing not just enterprise computing, but now also high performance computing. And we're seeing that, of course, with Google and Amazon and Azure and others. I was hoping you all would share more with me, maybe about the cloud providers and how present were they at SC this year?
They were very present. And, Google had a wonderful booth. I was able to talk to their HPC lead there, and the name escapes me. It'll come back to me in a second. But it was a wonderful. It's a wonderful transition. So for a long time, we've observed the cloud become this sort of rent a compute for a bit. But what we haven't seen is this concerted effort to make high performance computing part of it. So supercomputing is, like I said, from an application perspective, but high performance computing is, to the way that I define it, has to do with what Jay just said, which is this highly integrated system. So the network, works over thousands of nodes and has been purpose built for this job. And the GPUs that are in the nodes are purpose built and have high integration with the network itself. And the storage lives outside of the supercomputer, but it's also highly integrated to each of the nodes within the HPC. So to have this level of integration isn't really worth it for clouds, or hasn't been worth it for cloud providers up until now, as people kind of decided, well, maybe I should move my data center off from on-prem to the cloud, because now these services are being provided on the cloud. And well, maybe sometimes I need to have bursts of compute because I am an engine manufacturer, and these engine projects don't happen every single day, but I want to keep some stuff for everyday work. And then I want to be able to do these special projects and then do them somewhere else without having to buy or release a supercomputer or add power to my data center and all of these problems that come with having to install these on-prem. So the fact that the cloud manufacturers, not only are they gaining talent from a lot of these labs, not just at DOE, but worldwide, and basically hiring us out from the labs to run these systems and investing in highly integrated systems, shows that they see the promise of supercomputer, but also shows that the extra little push that was needed was AI. Like, AI has been a huge conversation even within supercomputing circles, and they see a benefit to building for both scenarios, whether you're doing simulation or you're doing AI, to have these highly integrated systems. So we sort of proved the concept since Summit and now with Frontier and others that this is actually worth their time and their talent and their money to be able to put these systems available to the general public.
Yeah, I think the big thing here is that the general public is starting to see the need for high performance computing, for at least basic number crunching, for data analysis, maybe for AI, and along with the clouds, there's a ton of new cloud service providers that are popping up, which is very interesting to see beyond the big three. And HPC has always been very foundational and open source. They've always really relied on open source packages and open source software for development, but it was very refreshing to see how mature that has become with the announcement of the High Performance Software Foundation that's coming out from the Linux Foundation. I think that's a really great way to start to tie together all these different open source projects from different labs, from different vendors, and help to build a new sort of foundational model for how to deploy HPC systems and how to manage them and how to build that software environment for everybody. So it's kind of a portable and common stack, no matter where you go. I thought that was it was very refreshing to see how far that's come along.
So I'm curious if anyone has ideas or opinions about why China did not appear at the top of the supercomputing list this year. Go ahead.
I have many opinions. So I quoted this last week in a completely different context, but I'll quote it here. I heard a while ago a philosopher that I follow, actually not a philosopher, but a poet that I follow on social media. I really love her work. And she said that the opposite of love is not hate, but it's apathy. And I think China is displaying that in full. It's saying, look, I'm just not even going to play in your games. You've decided what the game is. You've decided, you, meaning the US, have decided what the game is and who gets to be winner. And we're going to do our own thing. And China's always, as a nation, done their own thing. And they try to focus on their own people and sort of in the global stage to try to keep it themselves. But in this case, it was basically a big screw you, United States. We're not going to play your games. We're going to do our own thing. And you're going to be left wondering whether or not we actually have the fastest supercomputer, but we're just not going to show our colors. And so I think, to me, it's kind of a master move on China's part that to not even play, because it leaves everyone guessing, is the US at top, on the top at all? Because we know China's not even bothering to play.
Yeah, right now the West is the top of the official list. There's the one and only exascale computer, Frontier, but there were rumors that China has as many as 3 exascale computers running, and all sorts of interesting speculation. Are they still in the test mode, or do they have fully functioning ones they don't want to talk about because of a fear of more sanctions? But we were hoping to see them on the list this year, and they still, as Fernanda said, just are not playing with us. The rest of the world.
Push back a little bit on what Fernanda said about calling it a China versus US. The top 500, for all of its pros and cons as a benchmark is absolutely a global benchmark. I mean, I would say
It is.
that
No, the benchmark itself is
yeah,
global. I'm just saying that the fight has been between the US and anyone else that wants to play. And so the top numbers have been basically the US for a long time. And every time China wanted to play, they would either do some cloud provider like Alibaba or something like that. They would put in some sort of fractional part of their their cloud system, or play with some other component showing. And part of it, there was some ridicule too. I remember when they tried to come out with one of their chips, and the US folks kind of scoffed and said, haha, this is still like a 65 nanometers. This is old technology. But China's like the honey badger. China don't care. Like they're going to keep trucking. They're going to build the biggest bridge. They're going to build the biggest dam. They're just going to build, and they're not going to care whether or not you pay attention. So I think, to me, that's them signaling to the US, even though yes, it's a global benchmark, but it's really a signal to the US.
all right. Well, I want to get to a topic that we've somehow barely touched in this podcast so far, and that's AI. One of the fascinating things about high performance computing now is that generative AI models are trained on supercomputers, and yet you rarely see a mention of supercomputing in the article you read. You'll see, oh, this model was trained with 100 billion plus parameters, and it was trained for a month at a data center somewhere, but they rarely actually mention that system it was trained on is a high performance computing cluster. It is a supercomputer class system. So supercomputing really is hitting a new gear now when you add AI, and especially generative AI's boom, on top of the huge foundation of simulation and large scale data analytics. So I'm guessing there was a lot at SC23 about AI and maybe even generative AI on supercomputers. Is that right?
That was right. The term AI for science was a big conversation topic that kept coming up everywhere. Now, they said when they talk about AI for science, it's not necessarily the large language models that ChatGPT does. I mean, they're not trying to predict or generate a lot of text. They're trying to predict the results of scientific calculations without actually having to do weeks and weeks and months of them. So it's somewhat similar, but it's a different emphasis. And the DOE is certainly investing a lot in AI for science now.
Yeah, I think there's a lot more interest in the HPC community, whereas I think maybe there wasn't so much in the past. Okay, there was no interest in the past. It was black magic. It's not it's the dark arts.
There was downright disdain.
It's not a physical science, so it's hard to explain. I think we were talking about how we need a supercomputer today to do our weather simulation. There's a lot of talk today about building models that are just as performant and run on a single server, a single GPU. So some of those advancements are neat. I like what Mike is talking about, sort of augmenting HPC simulation, whether that's replacing, brute force libraries with models, or using models as input for your simulation. I think there's a lot of interesting things that people have talked about. One thing Mike pointed out, that Microsoft had a number 3 system on the top 500, and that's an NVIDIA accelerated system. Something that they didn't announce at SC, but announced the same week at their own conference, is they made their own ARM chips that are AI accelerators, one for an inference and one for training. So kind of a really interesting space that's evolving inside of HPC is now this, kind of organic growth of AI coming at it from all sides, from either from the hardware design and down to the software.
Yeah, I had a ton of conversations with folks, and one of my favorite questions to ask just about anybody, not just at conferences, is what are you working on that's interesting to you right now? And a lot of folks talk about, well, I'm working with this, and then eventually they would say, and we're working on building some foundational models. And I wrote a short blog yesterday on sort of the 2 buzzwords that I came across that were kind of new to HPC. is how many people were just talking about foundational models. And I think we're going to see a lot more in the coming days, partly because, NVIDIA dominates because NVIDIA got there first, essentially, right? So we installed Titan at Oak Ridge National Lab, and we helped NVIDIA build all these libraries, the entire CUDA, ecosystem that they have now. And so they dominate because they've built the libraries, but there's nothing stopping anybody else from taking over, so long as the ecosystem gets built. And AMD, kudos to them. I was very excited, and some private conversations I had, and some of the work that they're doing to build their ecosystem. And part of that was, again, work with, that they've done with Oak Ridge National Lab. And so it's not so much that I don't think other chips can take over. They can, and certainly Microsoft's chip can take over. And we just saw today Graviton at AWS Invent came out, and Graviton 4. They can all do it, given that there's an ecosystem and a set of libraries that can do that kind of work underneath, because nobody wants to go code libraries by hand. But what was great about seeing that is that the disdain for AI, going back to what was happening in the earlier years, it was all but gone. It was almost like an acceptance that, okay, well, maybe this isn't totally bonkers. And well, there's funding agencies that are willing to fund this work, and we're willing to experiment. And that is a huge step forward, because I do think that there's a place for AI. It's really hard to convince scientists that have been, doing this deterministic work or this deterministic kind of simulations to all of a sudden trust a black box. But more and more, they're coming to the realization that it could speed up their own work and, eliminating possibilities or generating possibilities. So they're not testing 200,000 molecules to see if it'll fit some sort of pocket in a cell, but they're testing maybe 15 at a very high resolution, a very high, performance simulation, and that they can see the benefit in that.
Yeah, and I've seen some interesting projects like the Science GPT that they're doing on Aurora right now, trying to build a trillion parameter model based on all of the DOE's code, papers, results. With the hope of, well, if we build a big enough model off of all of our previous research, maybe it'll help us accelerate our science. Maybe it'll help us think about new things faster, or come to faster conclusions.
And maybe it'll help port our Fortran codes.
That's the next step. Can we put this Fortran to Python and make it fast?
Now leave poor Fortran alone. I like Fortran. All right.
So Fortran.
We're going to get to a wrap up point here, and I want to ask each of you a different question. John, what is your advice for companies now in terms of embracing HPC? Coming out of SC, I know you talked to various industry customers there, but what is the high level, top level, recommendation you would give to companies that haven't yet started adopting HPC?
Folks that haven't yet but are thinking about it need to really lay out the business case for what they're going to do. And like Fernando was pointing out, there are options in the cloud world and other, colo service providers that you don't have to build everything in your own building and on-prem. But if you're thinking about adopting HPC, adopting AI technologies in your business, you need to start thinking about the power and cooling that's going to be required to run that and where you're going to put it. That's kind of one of the biggest changes that I see happening in this landscape is for the longest time, we've been racking and stacking pizza boxes or, off the shelf servers and building them into these large scale supercomputers. That I think that that model is drastically going to change the way I see the accelerators being built, the way we see the power usage going through the roof. It's no secret why there's so many water cooling companies now at supercomputing on the trade floor. Things are hot and things are powerful. So folks that are thinking about getting into it, start to think about facilities and where you'd host it.
And I just want to make one clarification for our listeners there. John is not saying that the technologies are becoming less efficient, just that we are leveraging more, and we're expecting more and more computational capability and aggregating more and more components. So of course, the total power goes up, right?
Yeah,
Mike, as someone from AMD that has some of the most powerful systems on the planet and someone who goes to lots of these SC conferences, what are you most excited about potentially seeing next year? What do you expect to see a big trend that may reveal itself at SC24 or may really achieve a threshold of big success by SC24?
Well, there's good competition in companies making the components, AMD, Intel, NVIDIA, but much less competition in companies that assemble these components with all the network and especially the emerging optical networks into the large supercomputers. So I'm waiting to see what happens in that realm. And Aurora should come fully online by then. So good to see where that turns out to be, because it's only about halfway in production right now. And the other big thing is, and this is a great opportunity for new companies, applying AI and machine learning to this field to greatly accelerate what's possible. I mean, AlphaFold was a perfect example of that for folding proteins that couldn't be done by brute force very well. But applying some machine learning, they solved that problem. And I expect to see a lot more of that happening.
All right. And Fernanda, I'm going to ask you my last question. And it is, why have you not mentioned quantum computing during this podcast at all? You knew I'd want to hear about it. What happened at SC23 and quantum computing?
There was a whole quantum village.
There was a quantum village, and it was very sad and stuck in the corner.
Way in the corner.
You're just baiting me, Jay, to rant on quantum. I don't hate on quantum, but it's a little whiles away for, I think, not just the technology. I think the technology actually could do some stuff now, but I think the public trust and just the overall kind of talent pool isn't available right now. You have to deeply understand quantum systems to be able to actually get some decent results out of it. And if you are not a physicist or a statistician to understand the sorts of things that come out of quantum systems, you're going to have a hard time trusting the results that come out of it. So that's I'm going to be diplomatic on this answer, and I'm going to answer the previous question, which is don't wait to get your own system. Start exploring now. You don't have to reinvent the wheel. There are applications that exist already. The people that have come before you and put those on the cloud. To pardon to my hardware vendors here on this podcast that are really hoping you build on-prem systems. The reality is you don't have to start from scratch, and you're going to outgrow the cloud. So once you start in the supercomputing path, it's a gateway drug to start on the cloud before you get yourself on-prem system, because you realize the costs are exorbitant. But go experiment, go have fun, go figure out what others are doing. And if you're a first in your field, go do it, because you're going to have definitely a leg up that other people are going to do. But be realistic about the actual results that come out of it. It's hard to find talent out there. It's hard to find people that understand, how to run the simulations. But there's lots and lots of help. Go to SC24 and find any one of us, and we'll point to people that we know and friends, and we'll get you in touch with them.
All right. Well, I would probably quibble with you a little bit, as you and I do, on quantum computing and its future, since I'm more of an optimist. But I do love you referring to cloud HPC as a gateway drug. So on that hilarious note, thank you for all of your insights. I hope our listeners have a greater appreciation for the role that high performance computing, and especially at the largest scale, supercomputing, plays in all manner of interesting business problems and societal problems and understanding the world around us. It's a huge enabler of AI. It's completely embraced by the cloud companies as well, because adoption of HPC is so high. All of the cloud providers are providing HPC services as well. The open source movement is alive and well in HPC. As John said, if you're about to begin this journey, remember power and cooling. You can start without a data center by now doing this in any of the clouds. But as you go to thinking about on-prem, as Fernanda thinks is inevitable, as you start really your journey, get deeper into your journey with HPC, think about that power and cooling and data center design to get the maximum value and cost efficiency out of it. Have I left out anything, guys? Anything we should share with our listeners before we go?
SC24 next year, Atlanta, Georgia. See you there.
Oh, thank goodness it's in the South and it's hot. As a Southerner, I appreciate it.
It's always a good time in Atlanta.
All right. Well, thank you guys very much. I appreciate you being on the Austin Forum Upload, and I look forward to talking to all of you again soon in our various other projects.
Thanks for listening to the Austin Forum Upload. You can listen to additional episodes and check out a schedule of our monthly in-person events at austinforum.org. The Upload is a production of the Austin Forum on Technology and Society, a nonprofit organization here in Austin, Texas.